So, in the previous class, we talked about the S matrix, that is SQ symmetric matrix, relating the time derivative of rotation matrix. So, I just want to summarize whatever that is very important with respect to the course. So, R dot of t means time derivative of the rotation matrix is S. That, remember, S was SQ symmetric matrix, omega t, and the R of t, that's right. And n effector rotation matrix with respect to the base coordinates matrix is, as you know from the previous classes, R1 respect to 0, 2 respect to 1, R3 respect to 2, and finally Rm respect to n minus 1. And by using this relation, we could establish finally the previous class that the angular velocity of the end effector of a robot with respect to the base coordinate system is angular velocity of frame 1 with respect to 0 plus rotation matrix of frame 1 with respect to 0 omega 2 with respect to 1 plus rotation matrix of frame 2 with respect to 0 omega 3 with respect to 2, and forever until we get n minus 1 with respect to 0 omega n with respect to n minus 1. Okay, by having this, now I want to solve for the first time a planar robot. So example is this. Example: suppose that you have this robot, guys. This is the robot you have that is working in the x and y plane. So here is x naught, your base coordinate system. In the robotics, you always, even that you're going to go to industry, sorry guys, you have to set up your base coordinate system, okay? And this is the one link. This is one link of the robot. I'm going to change the color to make it visible. And this is the second link of the robot. And this is the third link of the robot. Here we go. We have one joint here, one joint here, and one joint here. And here is what? End effector. Here is end effector that's picking up the object, like as the Baxter I have in the lab, okay? End effector, okay? So you have this rotation, theta 1, this rotation of this link with respect to this link, theta 2, and you have this rotation, theta 3, okay, theta 3. So based on the DH parameter and how to set up the coordinate systems, because this is rotating in this direction, as you see, theta 1, so z1 is in the axis of the actuator, so z naught, so it's going to be out of the page based on the right hand rule, that's right. And also the same here, z1 is out of the page, and the x1 is the normal to both of the z's and connecting them, so this is going to be x1 because they are both out of the page, so x1 going to be normal to them, that's right. So z out of the page, so based on the right hand rule, so this is going to be y, that's right, y1. Here is o1, obviously. Yes, let me change the color. So suppose that this is in this direction, okay? So again, z3 gonna be out of the page, and z2 is out of the page, so this is gonna be normal to those of them. See, this is x3, they are normal to this, and this is minimum distance, right? And obviously this is gonna be y3. Here we go. And this is the end effector. So it's gonna be again x3 and y3 and y3. I'm just putting like this, okay? Oh, these are 2's. I'm getting older, guys. I jump to 3. Oh, because I saw 3 here. These are 2's. Okay. So we set up our coordinate system. So you have to do that. Even in the backside, here in the lab or the quadruped robot, if you forget to set up a proper coordinate system, you cannot drive the coefficient of motion of robot. And when you don't have the correct model of the robot, you cannot control it properly. So this is Planar Robot. That's an example of whatever I taught until today. I'm gonna teach you Planar Robot and 3 degree of freedom. 3 degree of freedom. What are those? Theta 1, theta 2, and theta 3. We have 3 degree of freedom on the Planar Robot. Okay. So my question is, calculate end effector angular velocity with respect to the base. So your n is how much? Your n is 3. Understand? So I'm going to use this relation. So you're going to have omega 3 respect to 2 is omega 1 respect to 0 plus means rotation of the frame 1 respect to 0 plus r1 respect to 0 omega 2 respect to 1 this respect to 1 which is theta 2 with theta dot 2 plus r2 respect to 0 omega 3 n respect to n minus 1. N minus 1 is 2. Bingo. Understand? Again, angular velocity of the frame 1 respect to 0 is going to be theta dot 1. R1 respect to 0 omega 2 frame 2 respect to frame 1 which is theta dot 2. I'm going to express that. And 3 respect to 2 and this. Understand? So now let us write it here, guys. What is omega 1 respect to frame 0? Means the angular velocity of frame 1 respect to frame 0 with the base coordinate system. So what is that? It is theta dot 1. Theta dot 1. Frame O1, X1, Y1 is rotating with respect to your base coordinate system with this angular velocity. That's right. This is angular velocity, theta dot 1. In which direction? In which direction? Yes, obviously. Remember how we set up the coordinate system in the axis of z. So it's going to be k, unit vector. This is from dynamics, that's right. So we know this. Bingo. You have to do like that. Okay. So what is omega 2 respect to 1? Okay. Means angular velocity of the frame 2 respect to frame 1. Frame 2 respect to 1 is rotating by this angular velocity. Means theta 2. That's right. So we're going to be theta dot 2. Again, in which direction? In which direction? Out of the page. Right hand rule. Your thumb shows the axis of rotation, and the other 4 fingers by your right hand showing the direction of that. So it's going to be again k. That's right. Remember, x-axis has a unit vector of I. This is trivial dynamics. Axis y is the unit vector of j, and the k axis k is k. Not k. Z, x, y, z. X, y, z. That's right. Okay. So we got this. It's funny. And now omega 3 respect to 2. Angular velocity of the end effector of the robot respect to frame 2. All of these rotating with this. So you're gonna have, if that's that rotation, gonna be theta dot 3 again in the direction of k. Here we go. And I got this. Now we have to calculate this and this. I taught you this million times. Let's do it together. Okay. R1 respect to 0. Rotation matrix of frame 1 respect to 0. So R1 respect to 0. How are we going to do that? From the second class. directional cosine, that's right, directional cosines. This is rotation matrix, not homogeneous matrix. Just be very careful, okay? So x1 with respect to x0 gonna be cosine theta 1, trigonometry. Cosine theta 1, yes. x1 with respect to y0 gonna be sine theta 1. I hope that you know it. It's a trivial trigonometry. x1 with respect to z0, because z0 is out of the page, so gonna be, has no projection, 0. So y1, if you can transfer it here, you can transfer it here for simplicity, and you can say this is x1, you can transfer it here to judge it. y1 gonna be how much? This angle, so this angle gonna be also theta 1. That's right. These are trivial trigonometries. Gonna be minus sine theta 1. Minus sine theta 1. So y1 with respect to y0 gonna be cosine theta 1. And the y0 with respect to z0 is 0. But because the z of this out of the page, the z of these, they are the normal together. So what we're gonna have is 0, 0, and 1. Here we go. Understand? So now we got this. Yeah, we got this. Now R2 respect to frame 0. That's right. So R2 with respect to frame 0, as I taught you just today, or refresh your mind, you can calculate from here. That's right. Is R1 with respect to 0, R2 with respect to 1. So we already have this. Gonna be cosine theta 1, sine theta 1, 0, minus sine theta 1, cosine theta 1, 0, 0, 0, 1. Now what we're gonna do, we have to use the directional cosines to calculate R2 with respect to 1. Rotation of frame 2 with respect to 1. 2 with respect to 1. See, and you can transfer it for simplicity. Here we go. Change the color. Oh. Change the color. So you can transfer it here. It can be x2. This can be y2. That's right. Here is also theta 2. That's right. This is trigonometry. So x2 with respect to x1 meaning cosine theta 2. Cosine theta 2. X with respect to y1 gonna be sine theta 2. I hope that you know this from trigonometry. And 0, because the z's, they are the parallel here. Y1 gonna be minus sine theta 2. Minus sine theta 2. And y1 with respect to y0, y2 with respect to y1 is cosine theta 2. Here, projection here. Cosine theta 2, obviously 0. And the z's are again, sorry, the z's are, both these are out of the page. See guys, you have to, if you follow a logical path from assigning a proper coordinate system on the joints based on how we define the DH parameters, denoted Hartenberg parameters, and then apply one by one rotation matrices, this formula from the effector, you are fine until this point. Okay, and the z's, and respecting to the right hand rule, so these, the both are out of the page, so gonna be again 0, 0, and 1. So let me do this like so. If I want to calculate this, you're gonna have multiply this, right? Cosine theta 1 and cosine theta 2 minus sine theta 1 sine theta 2 and 0, 0. Now here minus cosine theta 1 sine theta 2 minus sine theta 1 cosine theta 2, 0, 0, 0, 0. You're gonna have a 0 here. Sine theta 1 cosine theta 2 cosine theta 1 plus cosine theta 1 sine theta 2. No, the next, minus sine theta 1 sine theta 2 plus cosine theta 1 cosine theta 2, and again gonna be 0. And finally 0 0 0 0 and 1. But we know that from trigonometry from high school, this is how much? This is cosine theta 1 plus theta 2. This is how we know. And this is gonna be from trigonometry of the high school, this is gonna be how much? Minus sine theta 1 plus theta 2. The same here, gonna be how much? Sine theta 1 plus theta 2. And again from trigonometry, we know that this is cosine theta 1 plus theta 2. So our 2 respect to 1 gonna be, and I'm showing this here as a cosine theta 1 2 for simplicity. I'm showing as minus sine theta 1 2 for simplicity. This is gonna be sine theta 1 2 for simplicity, and the same here. So the R2 respect to frame 0 of this robot gonna be cosine theta 1 2 minus sine theta 1 2 sine 1 2 cosine 1 2 0 0 1 0 and 0. Okay, this is only part of our solution because we just calculated this. Now we have everything. Now we have everything. So going to the next page, you can now say the angular velocity of end effector with respect to frame 0, which is a vector. Obviously it is, see, omega 1 respect to 0. What was that? Theta dot 1 k. So yeah, we have to write in the vector. Oops, freeze. So we have to write in the vector format. This in this direction, that's right, k. Theta dot k. 0 0 theta dot 1. Bingo. Plus r1 respect to 0 omega 2 1. Omega 2 1 is again in the along with axis k. R1 respect to 0, we have it from here. We just put in here. Gonna be plus cosine theta 1 sine theta 1 0 minus sine theta 1 cosine theta 1 0 0 0 1 multiplied by, this is r 1 respect to 0 by theta 2 respect to 0, which was 0 0 theta dot 2. Bingo. This is that. Plus we have third term. R2 respect to 0 in this. We have this and we just calculated this. So we're gonna have cosine theta 1 2 minus sine theta 1 2 sine theta 1 2, we just calculated, cosine theta 1 2 0 0 1 0 0 in omega 3 respect to 2 0 0 theta dot 3. Okay, understand? So this is obviously like that. Get here 0 0 theta dot 1. For those of you that you are weak in the linear algebra, this is 3 by 3 matrix and 3 by 1. So result gonna be 3 by 1 plus this by this 0, this by this 0, this by this 0. Here the 0. This by this 0, this by this 0, this by this 0. This by this 0, this by this 0, gonna be theta dot 2 plus again 3 by 3 matrix in 3 by 1 matrix vector 0. If you do that, I'm just skipping that because this is trivial. So the end effector angular velocity for this 3D graph reading planar robot is the summation of all angular velocities. Okay, summation of all angular velocities. So you see that this is planar robot. So this is shortcut for the planar robots, guys. At least at this stage I'm teaching. Just look at the vectors of rotations. Theta 1 axis of rotation is in the Z out of the page. Theta 2 axis of rotation is Z out of the page. Theta 3 axis is Z out of the page. That's right. So it's enough that you add them because they are at the same direction. Understand? They are at the same direction. So you answer to the dot 1, to the dot 2, to the dot 3. But if I say, for example, let me clean this, erase this. If I say that the robot is rotating like this, now the axis of rotation of this gonna be inside the page. That's right. Z2 gonna be inside the page. So these Z0 and Z1 they're gonna be out of the page. Z3 gonna be based on the right hand rule inside the page. That's right. So the angular velocity of end effector now gonna be theta dot 1 plus theta dot 2 minus theta dot 3. I wanted you as a homework based on this formula calculate that if I change the direction of this theta. But this is planar robot. You cannot judge always like this because in the Baxter I have in the lab, you can see from my website, if you have 3D rotations, you cannot judge like this. You have to go with this formula. Okay, understand? So this is a 3D grafting robot, and now we are fine. So before going to the next topic and then to the Jacobian, that is super important part of this course, let me teach you linear velocity of a point attached to a moving, is it recording? Yeah, moving frame. Okay, our famous space coordinate system. Here we go. O naught, X naught, Y naught, and the Z naught. And suppose that we have a frame here at the space. Say X1, Y1, and Z1, and I'm connecting the origins, and here's O1. Okay. So we know that the homogeneous transformation of frame 1 with respect to frame 0, remember, was R1 rotation matrix with respect to frame 0, and the origins, distance of the origins of 1 with respect to 0, zeros and ones. Remember homogeneous transformation that we had? Now suppose that we have a point on this rotating frame. Means that x1, y1, z1 is rotating with respect to x1, y1, z0 is rotating. So we know p1 means the position of this point with respect to the origin of O1. We're gonna find what, as this is rotating, as this frame is rotating around the base frame, we want to find what, p0, p with respect to 0. Based on whatever I taught you previously, you know that this is R1 with respect to 0, P with respect to 1, plus means expressing P1, okay, in this coordinate system, plus origin of these, plus O1 with respect to 0. Understand? So I'm expressing the position with respect to the point O1 in these coordinates by multiplying this, by multiplying the rotation matrix, and then plus these are vectors, that's right, these are vectors, plus origins of O1 with respect to 0, because as you see, look at here, this vector is this vector plus this vector, that's right. This vector is this, but let me change the colors because it's too much. This vector, this purple, is this, understand? And let me change the color of this also. Yeah, this is good. But this orange connecting O1 to O0, let me change the also color of this. This is this, understand? So now we can write like that, understand? But we want to have the velocity of point 1 to be expressed in the frame coordinate frame system. So what we're going to do, we're going to have time derivative from both sides. So we're going to have p respect to frame 0 dot vector gonna be r1 dot that I taught you in the previous class by skew symmetric matrix, p1, okay, plus o1 dot respect to 0. Everything is by time derivative. But today I taught you about these guys. Come on. See, I taught you this. R dot is S omega t RT. Here we go. I'm just writing here. So this is equal to S omega of t RT, R1 respect to 0. Here R is this. And P1 plus O dot 1 respect to 0. Right? So obviously this statement, or which is this statement, it is what? This is the position vector of point 1 expressed in the base frame. So I'm going to say R, okay, position of 1. So in multiplied by S omega of t plus O dot 1 respect to 0. Okay, but based on property I taught you in the previous class, please go and check. This can be written as, this is warming up, hold on guys. Okay, so based on which property? This property you have in your notes. Remember property number 1. We said S of vector A in P can be written as A cross product in P. You have your notes, right? So exactly you have this side. I'm gonna transfer to, you're gonna say omega multiplied by R, exactly like that. Your P here is R, your A is omega, right? So plus O dot origin of 1 with respect to origin of 0. I bet you have seen this in dynamics. So this is, I'm naming this as V, capital V vector, and I'm naming this as a small v vector. So we're gonna say V plus V. Okay, so if you know the position in space with respect to your frame and the frame is rotating around the base frame, you can calculate. This is very famous in the trivial dynamics. So let me explain this in these notations. R, which said R is R1 with respect to 0 P1 is the vector from O1 to point P expressed, as I said, in O0, X0, Y0, and Z0 frame, base frame. That's right. So this R is a vector from O1 to P expressed in this frame. And V, small v, that we set here, look at here, this is a small v, this small v is the rate which origin of that O1 is moving with respect to O0. Bingo, we got that. So, okay, now I can go to introduction now. Jacobian of a matrix, that is the most important part of the robotics. So after solving this 3D graph rhythm robot, we can go to Jacobian. Let me change the color. Note that finally we want to find position, say linear velocity, as I explained, and orientation means angular velocity. I mean that including angular velocity of and effector, we nothing as n, with respect to base frame. How we do that? By Jacobian. So H, remember, homogeneous transformation of M with respect to base in the space of the coordinate systems. Remember, Rm with respect to naught, Om with respect to naught, 1, 0. Remember that I told you that you're gonna have x dot and omega, x dot n linear velocity and omega and angular velocity is Jacobian of theta dot. These are for the links. Remember I explained it to you? So in this notation, Q, this Q is equal to vector of Q1, Q2, and the Qn transpose are joint variables, or angles. Okay, so now let me write this as this, because this is bizarre writing. Linear velocity means v. Okay, so as I said, we want to have x dot, as we had in the first class and the previous class, is equal to linear velocity of n vector with respect to the base frame, and the angular velocity of the n vector with respect to the frame, remember, was j q dot. This is general statement that we want to approach the Jacobian matrix. When Q dot, as you have seen in this example, theta 1, theta 2, theta 3, in the backstreet you have theta 7, okay? Gonna be vector of, oh, what happened? Nothing happened, long freeze. Okay, so is theta dot 1, theta dot 2, for Baxter theta dot 7, but I'm saying theta dot n. Suppose that you have n what? N links, n degree of freedom, sorry. So on the other hand, x dot is equal to, okay, we said is equal to v in respect to this, omega in respect to this. Now you can say that you can decompose this J, the Jacobian matrix, in this form, guys. In this form, J of linear velocity, J of what? Angular velocity. Understand? In Q dot. See? Here we go. So this promised to you that we're gonna have two parts for the Jacobian matrix. And this n by 1, obviously, and I said Jacobian matrix is 6 by n, always is 6 by n. Okay, if you have n degree of freedom system. Understand? Sorry, n links and joints. So next class I'm gonna go cover it, the Jacobian matrix.